A single missing or shifted line of atoms seems completely insignificant, but this microscopic anomaly generates long-range forces that dictate the macroscopic strength of a steel I-beam or an airplane wing. These anomalies are dislocations, line defects that severely distort an otherwise perfectly ordered crystal lattice. To understand how they affect a material, we need to calculate the stress they create. But right at the center of this defect, standard mechanical laws break down. This diagram illustrates the problem. Look at the red central region, the dislocation core. Here, the distance from the defect, R0, is roughly equal to the Burger's factor, B. The atomic distortion is so extreme that continuum theory and Hooke's law simply do not apply. But moving outward into the blue elastic region, the atomic displacement drops. The strains become small enough that we can safely apply Hooke's law to map out the forces at play. Our objective is to use this outer elastic region to calculate the stress tensors and determine the true energy cost of maintaining these defects within a crystal. To quantify the power of a dislocation, we have to look past the mathematical singularity at its core and measure the massive, far-field stress footprint it stamps onto the surrounding material. Forcing any material to strain structurally increases its internal energy state. We define this using the elastic strain energy equation, which relies on the product of the stress tensor, sigma ij, and the strain tensor, epsilon ij. To find the system's total elastic energy, we integrate this product over a specific volume element, represented by dV. This requires translating our linear atomic defect into a defined mathematical boundary. This geometric model solves the boundary problem by encapsulating the dislocation line within a hollow mathematical cylinder. We set an inner cutoff radius, R0, excluding the nonlinear core, and an outer radius, R, representing the elastic region's boundary. Constructing this cylindrical sandbox is the necessary first step to deducing the specific, localized forces generated by different types of atomic slips. We can now apply this boundary model to the first major defect type, the screw dislocation. This slide maps the displacement field for a screw defect. Atoms shift exclusively in the z direction, defined by W. Consequently, displacements along x and y, u and v, are strictly zero. The z-axis shift increases uniformly with polar angle theta around the defect. This one-dimensional displacement dictates the resulting stress tensor. The 3x3 matrix on the right organizes these stress components. However, there is a strict classification error in this engineering slide. Look at the geometric definition below the matrix. The cross product of the Burger's vector and dislocation line is 0. They are parallel, describing a screw dislocation. Analyzing these correct formulas, all normal dilatational stresses evaluate perfectly to 0. Because the atomic displacement operates completely parallel to the defect line, a screw dislocation creates a state of pure shear stress. It distorts the shape of the lattice, but it does not expand or compress its fundamental volume. The edge dislocation demands a far more complex mathematical treatment because its geometry is orthogonal. Looking at the mechanics, we see that atomic movement exists exclusively on the slip plane, along the x and y axes. Therefore, the z-axis displacement, W, is absolutely 0. This bidirectional in-plane displacement generates an incredibly intricate stress state containing non-zero values for sigma xx, yy, and zz. Unlike the screw defect, an edge dislocation produces both shear forces and normal dilatational forces, simultaneously pulling and pushing the lattice in multiple directions. This schematic illustrates how that stress state varies continuously depending on the polar angle as you move in a circle around the defect core. Because the sum of normal stresses is non-zero, the dislocation generates a hydrostatic stress field, defined here by sigma Hyd. The contour map shows the extra atomic half-plane acting like a wedge, crushing the lattice above into hydrostatic compression. Conversely, the lack of atoms below the slip plane stretches India apart, forcing it into a state of hydrostatic tension. This localized hydrostatic field actively drags foreign atoms, like carbon, into the tension zones to relieve stress. It is this precise interaction that turns edge dislocations into defect magnets, a mechanism that dictates the final yield strength of industrial metals. With the stress fields mapped and our cylindrical boundaries set, we integrate the tensors to find the total deformation energy. This graph charts total energy as a sum. We add the confined core energy to the much larger elastic strain energy. Notice how the elastic energy scales logarithmically. It overwhelmingly dominates the total energy cost compared to the small fixed core value. This table presents the final energy formulas. By superposition, the baseline elastic energy of any dislocation scales proportionally with the shear modulus, G, and the squared Burger's vector. But there is a crucial mathematical distinction in the edge dislocation equation, Poisson's ratio in the denominator. This acts as an energy penalty. Because edge dislocations create triaxial normal stresses, they require roughly 1.5 times more energy to exist in the lattice than a pure shear screw defect. This summary table confirms the overarching principle. Following the progression from the top row down, the initial geometric dimension of the defect dictates its displacement, which establishes the stress state, which ultimately calculates the final strain energy density. By mapping crystallographic geometry onto continuum mechanics, engineers can predict the immense localized energy costs of these atomic defects. It is the physics of these tiny imperfections that ultimately governs how structural materials harden, fatigue, and fail under pressure.